Now, in this video, we're going to be looking at how to write the matrix of a linear transformation. We've talked in a previous video about how to prove that a transformation is linear, but once we have the transformation, then we want to be able to represent it in matrix form if it is indeed linear. So we have a bunch of different examples we're going to walk through because depending on how the information is given to you, then you may need to do slightly different things in order to get that matrix. Sometimes it seems quite obvious, and other times it is a little bit less so. So we're going to begin by looking at the standard matrix for a transformation given a stated linear transformation in sort of mapping form. So here we have the mapping T, which maps a vector in R4 into another vector in R3, and it is given by this notation. So T applied to x1, x2, x3, x4 becomes this vector. How do we write the matrix of this linear transformation? So we can verify very quickly that this is in fact linear. There's no nonlinear components. There's no extra constants floating around. So this would be a linear transformation if we run a sort of a quick mental check. Okay, so once we have that, that means that we can write it as a matrix. So what will this matrix have to look like? Well, if we're transforming a four-dimensional vector into a three-dimensional vector, then the dimensions of our matrix will need to be 3 by 4. So if I were to take a four-dimensional vector and multiply it by this, there is one column for every entry to be multiplied by every entry in my X4. But in the end, I'm only going to get 3 entries to conclude with. So for instance, A11, A12, A13, A14 times X1, X2, X3, X4. And I have to set that equal to the entries in my original solution, 2x1 minus x4. So that suggests that for this to hold, A11 has to be 2, and A12 has to be 0 because there's no x2 in that expression. A13 also has to be 0, and A14 should be -1. Now, if we repeat this for each row of the matrix, multiply the next row by this, we get this expression. So that means A21 would have to be 1, and A22 would have to be 2, and A23 would have to be 1, and A24 would have to be 0 since there's no x4. And if we do this for the third row, we end up with A31 would have to be 0 because there's no x1. A32 would have to be -1. A33 would have to be 5, and A34 would have to be -3. And so if we set up our matrix like that, we end up with this matrix. Now, in fact, if we just go through our original example and pull out the coefficients, we get exactly the same thing. So if we go back to the top here, and I just write this statement, just like I would a coefficient matrix in matrix form, I fill in zeros where the coefficients are missing, 2, 0, 0, -1, 1, 2, 1, 0, 0, -1, 5, -3, I will get exactly this matrix that I found right here. So basically, just write the system that you get as a system, as a coefficient matrix in matrix form, and you're good to go. Now, if we're finding the matrix of the linear transformation here, we're mapping on R2 vector into R4, then our resulting matrix will be 4 by 2. And we can see, we can just pull out our coefficients for 5, 1, -3, 0, -1, 9, -6. And we're done. Now, Let's consider a slightly different example. We want to consider the polynomial in the standard polynomial basis, 4 plus 2t minus t squared. And we can represent this polynomial in P2 as a vector in R3 by pulling out its component coefficients and representing it as 4, 2, -1. Now, if we had a mapping that mapped P2 into, let's say, P3, where the transformation t is given by taking our prior polynomial and multiplying it by t minus 3, we can find the matrix that represents this transformation. So here it helps to perform the multiplication on a generic vector. So my generic polynomial, a sub 0 plus a sub 1t plus a sub 2t squared, and I'm going to FOIL through my t minus 3 transformation, and I'm going to get this collection. And if I collect terms, then my constants are just -3a0, and then my linear component is a0 minus 3a1, and my squared component, that should be a square, a1 minus 3a2, and then my cube component is a2. If I represent this as a polynomial in P3, I just put my coefficients in the corresponding positions. Remember, constant, linear, square, cube, and I would get this transformation, and therefore it is very easy to see that I can represent this transformation from this expression as a matrix with -3, 0, 0, 1, -3, 0. Again, this across is the number of dimensions I started with. Going down is the number of dimensions I'm going to end up with. No a0, 1, -3, and then in my bottom row, just the 1. As you can see here, we essentially have the linear multipliers of -3 here and the t multiplier coefficients here in this sort of not exactly on the diagonal since it's not square, but relative to each other. Now, here's another example. So suppose we have a function in the space defined by constant multiples of sine, cosine, sine 2t, and cosine 2t, which is to say all the functions of the form a1 sine t plus a2 cosine t plus a3 sine 2t and a4 cosine 2t. These are defined by 4 free variables, ai, and so this acts like a vector in R4. So consider the transformation defined by the derivative operation. What is the derivative? Well, let's do the derivative of our generic vector. We would get a1 cosine t minus a2 sine t plus 2a3 cosine 2t and minus 2a4 sine 2t. And if we put them in the same order as the functions in the original y of t, we would get this expression. So I move the sine up and the cosine back, and so on. Now, if we recall the locations in the vector for the trigonometric functions themselves, again, sine, cosine, sine 2t, cosine 2t, then our coefficients look like this, and we can represent, just again, pulling them out of the equations, and then we can represent this as a matrix that looks like so. So, again, we would have -1 a2. This would be just be a1 itself. This would be -2 a4, and this would be our 2 a3. Now, if I take any vector representing a function that has these components, and I multiply the vector of the coefficients by this matrix, that will take the derivative of the matrix of the function essentially and tell me what the new coefficients have to be. And in fact, I could do this several times if I wanted and take the second, third, and fourth derivatives, since the function bases themselves are not changing, only the values of the coefficients. Now let's consider the function defined on the above on the same space and consider instead the antiderivative function. And again, we're going to insist here that the constant of integration is 0 just to make things properly linear. So here, if I do my antiderivative of my string of functions, I'm going to get negative a1 cosine t plus a2 sine t and minus 1/2 a3 cosine 2t and 1/2 a4 sine 2t, which will give me this as the result of my transformation. And so similarly to my previous example, I can represent these as a matrix. 1a2 goes here, negative a1 goes here, 1/2 a4 goes here, and negative 1/2 a3 goes here. And again, just kind of keep in mind that once you do the antiderivative, you then have to make sure that your coefficients are in the order that we originally represented the bases, so sine, cosine, sine 2t, cosine 2t. And since these are supposed to cancel out, what should happen is if you multiply this antiderivative matrix by your original derivative matrix from the previous example, you should get the identity matrix. Now, in addition to these methods, there are also some common linear transformation forms that we can also kind of keep in mind. So we have a rotation matrix. This is for the counterclockwise rotation. For the clockwise rotation, the sign would move down here. So if you're told to write the transformation of a matrix for, let's say, a pi over 3 rotation, then you would simply evaluate cosine and sine at cosine of pi over 3 and sine of pi over 3 and fill in the corresponding values. If you're doing expansion or compression, then in one direction or the other, so here I would be expanding in the x direction by a or rescaling in the x direction by a, and here I'd be rescaling in the y direction by b. They can be the same value, they can be different values. If one of them is 0, then this is called a projection matrix because it reduces the non-zero component of the resulting vector from what it was before to at least one dimension less. And this is true for that matrices as large as you'd like. Just on the diagonal entry, that is your scaling factor. Rotation matrices are always two-dimensional, so they're rotating in a plane. So even if you have a three-dimensional matrix, if you're rotating in, say, the xz plane, then this would be the components in the corresponding x and z columns and rows. And then the y column would be an identity, let's say. Now, reflections across the x-axis look somewhat like the rotation matrices for some of these sort of 90-degree rotations, although they're not necessarily exactly always the same, but there's, a relationship to kind of keep in mind. So if x1 is equal to x2 or x1 is equal to negative x2, then you want to flip essentially your x1 becomes x2 and your x2 becomes x1. That is a reflection. The negative reflection would look like that. Again, the same thing, but opposite signs. Shear matrices are going to look like this, where they have typically ones on the diagonal and then the shear factor either in the top right or the bottom left, depending on whether they're shearing in the x1 direction or the x2 direction. If it's up here, it's shearing in the x1 direction. If it's up down here, it's shearing in the x2 direction. And so again, what are you thinking about here? Typically, you're thinking about like if you start with a square in the plane, when you shear something, you're essentially pushing over the top of it into some kind of a rhombus. The base remains fixed, but the top of it gets slided over. Now, as I mentioned, if you want to build a three-dimensional situation, some of these will generalize to 3 dimensions without too much of a problem. But in the rotation matrix, for instance, here we're rotating in the XZ plane. So our rotation components are in the first and third columns. And then the identity would go in the missing dimension, because when you're rotating, you're always rotating just in a plane and the other component remains fixed. Now, if you have a series of transformations as you would like to do in sequence, then you can multiply the matrices together in order to get a more complex series of transformations. So here's an example. Again, we want to find a matrix that transforms a vector in R2 to another vector in R2 through a rotation of 30 degrees, or pi over 6. And then we want to reflect it over the line x1 equals x2. And then we want to stretch the x2 component by a factor of 2. So first things first, come up with all of your transformations. So here's our rotation matrix, where I took my cosine minus sine, sine, or this is a clockwise. So cosine, sine, minus sine, cosine, and I evaluated all the thetas at pi over 6. Again, clockwise, the minus sign is down here. Counterclockwise, the minus sign is up here. The reflection matrix is this one. And then the scaling matrix for x2 only is going to be this. Again, we're not affecting x1. We're only stretching in x2. Now, think about how you would apply these in order. So first, you would apply your vector in R2 to this rotation matrix. And then the result, you would then multiply by the next one. And then the result, you would multiply by this one. Now, in this particular orientation, we're actually scaling first, then reflecting, and then rotating. But if you multiply them all together, then you get this composite matrix, and that will perform all of these transformations simultaneously. In some cases, you do need to be a little bit careful about the order that you multiply these transformations in, because, of course, matrix multiplication is not commutative. And so if you multiply in one direction versus the other, you may get a slightly different answer.